Okay, let's start. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Very good morning, all the participants. And selamat pagi. So I would like to extend our gratitude to all distinguished guests, speakers, all participants, ladies and gentlemen, in this very special occasion of the international webinar series to celebrate the anniversary of Mulawarman University and Faculty of Engineering as well. My name is Fahrizal Adnan. I am the chairman of the webinar today. First of all, before we start the webinar, let's start to give attention to the Indonesian anthem, followed by the hymn of Mulawarman University and Faculty of Engineering as well.
pakai ini wah. Nggak usah pensil, nggak boleh pensil ini lain.
Fakultas Teknik beriman dan bertakwa pada Tuhan yang Maha Esa, berwawasan lingkungan, berasas Pancasila, berbineka tunggal ika. Fakultas Teknik selalu berinovasi, mengembangkan potensi lokal, bermutu dan relevan, berilmu keteknikan, berkembang dan terdepan. Universitas Mulawarman Jaya, Fakultas Teknik bangga memberikan prestasi yang gemilang bagi nusa dan bangsa, membentuk lulusan teknik yang ahli, mandiri dan terampil di bawah panji-panji Fakultas Teknik. Segenap jiwa bantu baktikan.
Selamat datang di Fakultas Teknik Universitas Mulawarman. Selamat datang di Center of Excellence for Tropical Studies. Pengembangan pendidikan keteknikan sudah dimulai sejak berdirinya Universitas Mulawarman tahun 1962, ditandai dengan adanya Fakultas Pertambangan yang berkedudukan di Balikpapan. Namun kemudian fakultas ini ditutup karena kesulitan koordinasi dan penyediaan sumber daya. Tahun 1999 dibuka lagi program studi D3 Teknik Pertambangan di bawah unit pelaksana program studi diploma. Tahun 2003 pembukaan program studi S1 Teknik Pertambangan, Teknik Sipil dan Teknik Industri yang diikuti pembentukan unit pelaksana Fakultas Teknik. Tahun 2004 program studi D3 Teknik Pertambangan digabungkan ke UP Fakultas Teknik, dan tahun yang sama juga dibuka program studi S1 Teknik Lingkungan. UP Fakultas Teknik didefinitifkan menjadi Fakultas Teknik pada 27 September 2007 yang merupakan hari kelahiran Fakultas Teknik. Tahun 2010 program studi S1 Teknik Kimia mulai dibuka. Tahun 2014 Mendikbud RI memberikan mandat dan izin 6 program studi yang menjadi jalan dibuka dibukanya program studi S1 Teknik Geologi dan S1 Teknik Elektro. Tahun 2019, Universitas Mulawarman adalah salah satu dari 43 perguruan tinggi yang diberikan mandat dan izin program studi program profesi insinyur. Penyelenggaraan PSPPI melalui Fakultas Teknik telah menerima mahasiswa dan meluluskan insinyur-insinyur yang profesional di bidangnya. Tahun 2020, 2 program studi dari FKTI digabungkan ke Fakultas Teknik, sehingga jumlah program studi yang dikelola Fakultas Teknik adalah 10 program studi S1, 2 program studi D3, dan program profesi insinyur. Fakultas Teknik adalah fakultas ke-9 dari 13 fakultas di Universitas Mulawarman yang terletak di kampus Gunung Keluas, Samarinda. Dengan jumlah mahasiswa mencapai 3.500 mahasiswa, dalam kurun waktu 2 dasawarsa, Fakultas Teknik telah menjelma menjadi salah satu fakultas besar di Universitas Mulawarman. Visi Fakultas Teknik menjadi institusi pendidikan tinggi bidang ilmu teknik berstandar internasional yang mampu menggali dan mengembangkan potensi sumber daya alam khususnya hutan tropis lembap dan lingkungannya. Maka, Fakultas Teknik bertekad untuk menjadi yang terdepan dalam mengembangkan tropical engineering. Upaya mewujudkan visi Fakultas Teknik untuk menjadi yang terdepan dalam mengembangkan tropical engineering pada 2030, maka FT Unmul telah menyusun dan menetapkan 6 strategi utama. Strategi yang pertama adalah menetapkan pohon penelitian rekayasa tropis pada semua bidang keteknikan di Fakultas Teknik. Strategi yang kedua adalah menetapkan roadmap publikasi bereputasi nasional dan internasional hingga 2030. Strategi yang ketiga adalah menetapkan roadmap akreditasi nasional dan internasional hingga 2030. Strategi yang keempat adalah terus mengembangkan kualitas sumber daya manusia, khususnya dosen. Strategi yang kelima adalah terus mengupayakan terwujudnya rasio dosen dan mahasiswa yang ideal. Strategi yang keenam adalah mewujudkan tata kelola yang baik, akomodatif, adaptif, dan transparan. Fakultas Teknik pasti bisa.
Thank you. All participants, ladies and gentlemen, it is honor to me to be a moderator today. I would like to extend our gratitude as well to the come to the Zoom meeting, and for your information, we also live YouTube. Have live YouTube. It's around 33%, and the Zoom meeting is around 130. Let's continue to the presentations. It's honor to me to introduce to you the first speakers of today, Amit Kumar Maharjan. Amit Kumar Maharjan is PhD Fellow at University of Yamanashi. Amit Kumar Maharjan is PhD Fellow at the University of Yamanashi. He got scholarship from the M.Sc, Japan, and he will present to you. The first presentation is about groundwater treatment by biological processes. Amit Sensei, could you hear me? You are still in the mute mode.
Sorry. Yeah, is it okay now?
Yeah, it's okay now.
Yeah, okay, thank you.
You have 20 minutes to the presentation sessions. I give the floor to you.
30 minutes?
Yes.
30 minutes or 20 minutes?
20 minutes. 20.
Oh.
But we have the spare time. It's okay.
Oh, okay, thank you. Yeah, is it okay to share my screen?
Yes, please.
Yeah. Can you see my share slide?
Crystal clear.
Okay. I get this one. Sorry, I get this one in the center, man. Okay. Yeah. Good morning, everyone. Namaste from Nepal, and Ohayou gozaimasu from Japan here, and Salamat Pagi to all the Indonesian people here. And thank you, moderator, for my introduction. First of all, I would like to congratulate and express my best wishes on the occasion of 17th anniversary of Faculty of Engineering and 50th anniversary of Mulawarman University. Today, I would like to share a part of my PhD research with the topic nitrogen removal from ammonium contaminated groundwater by dropping nitrification and constructed wetland. These are the contents of my presentation. First of all, I would like to start with the famous quote of famous poet Auden on water. He said, "Thousands have lived without love, not one without water." It shows the importance of water for life. Water is classified as surface water, that is above ground, like rivers, lakes, etc., and groundwater, that is subsurface or located underground in large aquifers. Groundwater accounts for only about 1.7% of the total water on the planet or Earth, but is preferred for domestic supplies to the surface water because of consistency in quality and availability in sufficient quantity. About 50% of the drinking water supplies in the world is based on the groundwater, but the groundwater is found to be contaminated with ammonium, nitrate, arsenic, iron, turbidity, coliforms, etc. to various levels in different areas of the world. Here I focus my study in ammonium contamination because ammonium remains in the groundwater for a longer time due to hydrogeochemical conditions and cannot be removed by simple filtration procedures. And ammonium gets contaminated in groundwater through various natural processes such as geological degradation of organic matter, nitrogen fixation in soil, and during lightning, and anthropogenic processes such as excessive use of urea, animal manures containing urine, domestic and industrial sewages, leaches from landfill sites, and etc. Through one or above of the routes, groundwater gets contaminated in certain parts of Australia, China, Vietnam, India, and Kathmandu Valley of Nepal to substantially higher levels than that prescribed by the WHO guidelines for drinking water. Though severe health hazard of ammonium contamination has not been reported yet, but contamination with ammonium makes water undrinkable due to bad taste and odor. It also affects chlorine disinfection in conventional water treatment systems, increasing the possibility of pathogenic contamination in the water during treatment or during distribution systems. Moreover, there is the possibility of ammonium oxidation to nitrite and nitrate, which can cause methemoglobinemia, also known as blue baby syndrome in infants and pregnant women. Also, there is a possibility of producing N-nitroso compounds. N-nitroso compounds, which are potentially carcinogenic in human digestive tract. Hence, the treatment ammonium removal is necessary before conventional water treatment or distribution. Several physicochemical processes and biological processes have been developed for ammonium removal from water and wastewater, but biological processes are preferred because of low cost, simple in operation and maintenance, and no toxic waste generation during the process, also so-called the environment-friendly options. But there are very few studies that have considered biological processes for groundwater treatment by biological processes. And the removal mechanism is still unclear, which is the motivation factor for this research. So objective of this research is to study nitrogen removal from ammonium contaminated groundwater by biological processes, namely dropping nitrification and constructed wetland. However, we will not be dealing with the other contaminants in the groundwater like turbidity, coliforms, etc., and the cost estimations of the system. Going to the drop-in nitrification system, it's a low cost, simple in operation and maintenance, and for construction as well, it's an attached growth biological system working under the principle of trickling filters, and also the simulation of downflow hanging sponge system, which is found to be efficient in reduction of organic matter, nitrogen, and pathogens from sewage and industrial wastewater. However, the performance of the system was still not studied for groundwater. Hence, our objective was to study nitrogen removal from ammonium, investigating nitrogen removal mechanism and microbial community characterization from top to the bottom of the units. In this experiment, we used polyolefin sponge cubes of size 10 mm that were connected diagonally to make 1 meter long, and the synthetic groundwater of 50 mg per liter ammonium nitrogen was trickled from top to bottom of the units at 4.32 liter per day for 56 days in 4 replicates, and water samples and sponge from the top, intermediates at 0.25 meter spacing, and bottom were collected for monitoring nitrogen concentrations and microbial functional genes analysis. This shows the result of temporal variation of nitrogen concentrations in dropping nitrification units. Black line here shows the influent ammonium concentration around 50 mg per liter, and blue line is for the effluent ammonium concentration. From here, we can see ammonium removal started from the initial days and achieved stable state after a week of operation, and the removal efficiency ranged in about 60% ammonium removal. Here, we can see nitrite concentration in the red line, which increased rapidly till the 4 weeks period, then it started to decrease. Whereas the green line shows the nitrate concentration, which increased steadily to the end, till the end of our operation. And the removal of ammonium is equivalent to the production of nitrite and nitrate in the effluent, which indicates the occurrence of nitrification. And the results of pH like redox potential and the dissolved oxygen in the influent and effluent also supported the nitrification activities. And accumulation of the nitrite and nitrate in the effluent showed that there is no or very less denitrification in the drop-in nitrification system. And the second figure shows the temporal variation of nitrifying functional genes, ammonia oxidizing bacteria, AMOA, and nitrite oxidizing bacteria, NXRA. Here, we can see the abundance of AMOA was higher from initial days and increased rapidly within 2 weeks. So the ammonium oxidation to nitrite increased very fast within the few or 7 days of the operation, whereas nitrite oxidizing bacterial functional gene NXRA increased very slowly and steadily to the end, which oxidized nitrite to nitrate. And with the variation in the abundance of AMOA and NXRA was in agreement with the variation in nitrogen concentrations in this first figure. Like ammonium oxidation started from the first stage, and nitrite oxidation started after around 4 weeks of the operation, similar to the abundance of nitrifying functional genes. This shows the spatial variation of nitrogen concentrations in left and nitrogen transformation transforming functional genes in the right from top 0 meter to bottom 1 meter depth of the sponge units at 2 weeks interval, which I summarized in the next slide. Here, the ammonium removal from the top to bottom followed was best fit ammonium concentration for single order of ammonium concentration as shown in this formula. From this equation, we can estimate the length of dropping nitrification units for the removal of ammonium nitrogen, which will be useful for the engineering design of the dropping nitrification in actual field. This shows the relative abundance of microbial community at order level from top to bottom of the top 0 meter to 1 meter of the sponge unit on the last day of or 56th day of operation. We can see higher abundance of nitrosomonadales, that is ammonia oxidizing bacteria in the top half upper section, and found to be decreasing towards the bottom, whereas nitrospirales, this is the in yellow color, is found to be present from the mid section and then increase towards the bottom. Here I summarize the ammonium removal mechanism in dropping nitrification unit symbolically. In the upper part, we can see higher abundance of the nitrosomonadale to nitrite in the upper half, whereas nitrospirales, that is nitrite oxidizing bacteria, and higher oxidation of nitrite to nitrate in the lower half, as shown in the reactions first and reaction second. From this, we can say that the oxidation of ammonium to nitrite and nitrite to nitrate by ammonia oxidizing bacteria and nitrite oxidizing bacteria are spatially separated from top to bottom of the dropping nitrification units. From these, I concluded like dropping nitrification can remove ammonium from groundwater without external aeration, and we achieved nitrification only, and no denitrification was achieved in the patient. The ammonium oxidation to nitrite by AOB and nitrite oxidation to nitrate by NOB are spatially separated. Here, the ammonium removal was around 60% only. So I recommend to optimize the ammonium removal in dropping nitrification by studying at different flow rates and at various ammonium concentrations. And also we cannot achieve denitrification. So I recommend to study the nitrogen removal by dropping nitrification in combination with denitrification or Anamox systems. Now going to the constructed wetland. Constructed wetlands are the engineered systems designed and constructed by utilizing the natural processes with the interaction between plants, media, and associated microorganisms to remove organic matter, nutrients like nitrogen and phosphorus, pathogens from wastewater. It is a simple and low energy consuming system, but there are very few studies for the treatment of groundwater. So our objective of this experiment was to study nitrogen removal from ammonium contaminated groundwater by examining the effect of flow type, tidal flow and continuous flow, by investigating the effect of common reed plants in the nitrogen removal, and by studying the effect of plant roots in denitrification activity. To study the effect of flow type, constructed wetlands were prepared with 8 liters of zeolite and common reed plants. In tidal flow, 4 liters of synthetic water was filled in the okay, the animation I couldn't show here. Animation, I don't know. Was filled in the yeah, it's okay. 4 liters of synthetic water was filled in the wetland, and the inlet was sort of by timer. so that the water was kept in the contact with the media for 21 hours. Then the water was drained. Then after draining, it was kept in rest for 3 hours. Like we followed the cycle of fill 4 liter of water, and then kept in contact for 21 hours in the reactor wetland. Then it was drained. Then after draining, it was kept in rest or dry for 3 hours. This is the cycle for the tidal flow wetland. And in case of continuous flow, the flow was the synthetic water was allowed to flow at constant flow rate of 4 liter per day. Both the sets were operated for 105 days in 2 replicates, and nitrogen concentrations of influent and effluent were monitored every week. Nitrogen removal potential of zeolite microbe association in the tidal flow and continuous flow was studied every 14 days. This slide shows the changes in nitrogen concentrations in influent and effluent of constructed wetlands operating in tidal flow and continuous flow. Here, ammonium was not detected in the effluent of tidal flow throughout the experiment period, whereas ammonium concentration started to increase in continuous flow constructed wetland after around 21 days of operation. From this, it shows the ammonium removal in tidal flow constructed wetland was significantly higher than that of continuous flow constructed wetland in long run. It was due to the tidal flow operations, which supplied higher or sufficient oxygen for the rapid or complete nitrification of ammonium nitrogen in tidal flow constructed wetland. To study nitrogen removal potential of zeolite microbe association, 100 gram of zeolite from tidal flow and continuous flow, the previous experiment, was collected every 14 days. I skipped the methodology here, and the results, the changes in nitrogen concentrations and tidal flow and continuous flow have been shown in this graph. From this, we can see the ammonium removal of association was higher in tidal flow constructed wetland than in continuous flow. And ammonium removal during 2 to 3 hours of the experiment, first 2 to 3 hours, was higher and followed first order kinetics. And the removal in the zeolite microbe association is due to the nitrification and adsorption. But here was no nitrite and nitrate detection during the 2 to 3 hours. So ammonium removal in this 2 to 3 hours duration is basically due to adsorption only. So the first order ammonium removal rate in this 2 to 3 hours is equivalent to ammonium adsorption rate, which I summarized in the next slide. From this slide, we can see higher ammonium adsorption rates in initial days, which decreased gradually in both wetlands as the adsorption capacity of zeolite or any other adsorptive material is finite. This could be the reason of higher ammonium removal in constructed wetlands, continuous flow constructed wetlands for initial 21 days and then decreasing with the days of operation. But the ammonium adsorption rate of the association was significantly higher in tidal flow constructed wetland than continuous flow constructed wetland for longer time. The tidal flow constructed wetland, tidal flow operations might have supported the in situ biological regeneration of adsorption capacity of zeolite in tidal flow constructed wetland. Then to study the effect of common reed plants, small scale constructed wetlands were prepared with 1 liter of zeolite with and without plant. Both wetlands were operated as tidal flow of fill, contact 21 hours, drain, and rest 3 hours as of previous cycle. Nitrogen concentrations were monitored for 24 hours after 60 days of operation, and zeolite media and common reed roots were collected to analyze nitrogen transforming functional genes and microbial community characterization and study the denitrification activity. Changes in nitrogen concentrations in tidal flow constructed wetland with and without plants is shown in this slide. Here we can see ammonium decreased rapidly in tidal flow with plants, and nitrite was not detected, and nitrate increased for 2 hours and completely removed within 18 hours here. Whereas in case of wetland without plant, the ammonium removal was slower in comparison to with plants, and the accumulation of nitrate in that without plant. Here we can see the accumulation of nitrate, nitrification, but nitrate was accumulated here. So total nitrogen removal in constructed wetland with common reed plants is significantly higher than that without plants. And rapid ammonium removal in wetland with plants could be due to the plants provide oxygenated zone around the roots for the nitrification, and difference in the total nitrogen removal or higher nitrate removal in wetland with plants could be due to the occurrence of denitrification in the wetland with plants. Here this shows the abundance of nitrogen transforming functional genes in wetlands with and without plants. Here we see the gene abundance of was 2 to 3 orders higher in wetlands with plants than without plants. It's because the plant roots act as active sites for the attachment and growth of microorganisms, and plants also support to create aerobic and anaerobic conditions in the wetlands, which supported the growth and activities of nitrifying like AMOA and NXRA, and denitrifying NARG, NIRK, NIRS, and NOSZ genes. From this, we see the presence of nitrosomonadales, that is ammonia oxidizing bacteria, nitrospirales, that is nitrite oxidizing bacteria, and denitrifying bacteria like rhizobials and rhodocyclales in both the wetlands with and without plants. To study the effect of plant roots in denitrification activity, zeolite material and common reed roots were collected from tidal flow wetland with and without plants after 60 days of operation, and it was performed in anaerobic condition in bile. I skipped the methodology. Here the results shows that the denitrification activity or nitrate removal was higher in the vials with common reed roots. It is because the common reed roots release organic carbons such as phenols, organic acids, sugars, amino acids, etc. through rhizodeposition, and the organic carbons act as electron donor for heterotropic denitrification. From the wetland experiment, I summarized the removal mechanism in zeolite-based tidal flow constructed wetland. As we already discussed, it operates in the cycle of fill, contact, and drain, and then rest. During the rest condition, the wetland or the media absorbs oxygen. The zeolite absorbs oxygen from atmosphere. As the wetland gets filled, the ammonium in the water gets adsorbed on the surfaces, on the negatively charged surfaces of the zeolite. As ammonium comes in contact with oxygen that was previously absorbed during the rest condition, ammonium gets nitrified or oxidized to nitrite by nitrosomonadales, and again subsequently to nitrate by nitrospirales. After the consumption of dissolved oxygen by microbial activities for organic matter decomposition and nitrification, and long contact time in the 21 hours of long contact time, the wetland acts as anaerobic. And finally, the denitrifying bacteria of order rhizobials and rhodocyclales denitrify the nitrate heterotropically to nitrogen gas, with the organic carbons released by common reed roots. From this experiment, I concluded that zeolite-based constructed wetlands, tidal flow constructed wetlands, are efficient and sustainable option for nitrogen removal from ammonium contaminated groundwater without external aeration and organic carbons addition. Plants increase the nitrogen removal efficiency and plant roots supported denitrification in wetlands, and the removal mechanisms in the zeolite-based tidal flow constructed wetland were nitrification, denitrification, and adsorption. After this experiment, I recommend to evaluate the performance of zeolite-based tidal flow constructed wetland in actual ammonium contaminated groundwater in pilot scale. This slide summarized my presentation. Like dropping nitrification showed that it can remove ammonium from contaminated groundwater without external aeration. We achieved nitrification, but no denitrification, so accumulates in effluent. Hence, the dropping nitrification is suitable only if the ammonium concentration is lower, such that the produced nitrogen oxides, nitrite and nitrate, are within the drinkable limits of the WHO guidelines. And from the constructed wetland experiment, it showed that the zeolite-based tidal flow constructed wetlands are efficient and sustainable technologies for the removal of nitrogen without external aeration and organic carbons addition. This, for more information, please get where I have put both the papers, amit_kmr@hotmail.com. Yeah, that's all for my presentation. Thank you for your attention. Namaste. Thank you very much.
Okay. Amit Sensei, it's very great presentation from you. Let's reach some. Let's resume for the presentation. So, Amit Sensei research is about two things. It's about the nitrification dropping, and the second one is the constructed wetland using the zeolite, and then put some plan to also treat the ammonium contamination in groundwater. So, Amit Sensei, we would like to open Q&A session because the Dr. Zul has a problem for the connection. So,
Okay.
Okay. So, please, I will read some question. The first one is for the first treatment process using the dropping nitrifications. What is the obstacle of this research? What is the obstacles of this research in the dropping?
Yeah, the major limitation in the biological treatment processes, mostly the problem is with the aeration. That cost is with the aeration. In the dropping nitrification, we could achieve the nitrification without aeration, but the only nitrification was achieved, so that we can use this dropping nitrification system in the context of low ammonium concentrations, like less than 11 mg per liter of ammonium nitrogen, so that the produced nitrite and nitrates are within the limits of drinking water. This is the limitation in the dropping nitrification experiment.
Okay, thank you. Let me translate to the Indonesian language. Jadi Bapak Ibu dan peserta sekalian, jadi penelitian dari Dr. Amit ini adalah terkait dengan pertama melakukan pengolahan amonia dengan melakukan dropping nitrification, berarti dia arahnya itu adalah aliran dari atas ke bawah. Lalu yang penelitian kedua tentang constructed wetland atau rawa buatan, di mana pengolahan yang pertama ada beberapa kendala, yaitu adalah aerasinya, karena kalau misalnya kita mau optimal di proses nitrifikasi, maka aerasi menjadi penting. Yang kedua, pengolahannya adalah terkait dengan constructed wetland, dengan rawa buatan, dengan menggunakan zeolite dan tanaman untuk menghilangkan amonia juga. Jadi penelitian ini sangat menarik. Kenapa? Karena kita melakukan penelitian pengolahan air limbah dengan cara biological process atau pengolahan dengan cara biologi, di mana ini lebih ramah lingkungan, tidak berbahaya bagi lingkungan dan seterusnya. Okay, Dr. Amit, Amit Sensei, I would like to read the second question. For the dropping nitrification, it's followed by the first order equations. So what is the most influence variable in this first order equations? What is the most influence variable in the dropping nitrification process in your research?
Just a second, okay? I will share this slide again. You mean this slide, right?
Yes, yes.
Yeah, in this one, the ammonium removal from top 0 to the bottom of the dropping nitrification followed first order kinetics. That depends directly with the concentration of ammonium. If the ammonium concentration is higher, the removal rate is also higher. And if the concentration is lower, the removal rate is lower. So if you know the concentration of ammonium in the groundwater or the water, then you can put the concentration here, and you have the kinetic rate constants from the equations of the first order kinetics. And with this, we can estimate the length of the dropping nitrification that require for the removal of ammonium. If the concentration is higher, the ammonium removal may be faster or within the shorter duration of the length, whereas if the concentration is lower, the removal may be slower. Here, I just show the results here. The ammonium removal is higher in the top half because the concentration was higher in this section. After that, the removal rate is slower. The concentration decreased, so the removal rate is slower. This is the application of the kinetics in engineering field. We can estimate how long we need the dropping nitrification units.
Okay, thank you very much for the answer. So the most variable is about the concentration of the ammonium. So if we know the initial concentration of the ammonium, we can estimate the length of the reactor. So,
yeah.
The next question is for the construct wetland.
Terbanting sudah HP-nya. Astagfirullah.
For the constructed wetland, you use the synthetic groundwater, so you know the initial concentrations. And then, did you use the batch and continuous flow in this constructed wetland?
Continuous flow, and another is tidal flow.
Oh, okay.
I couldn't show the. I had animation here. I will try. Okay, here the water is filled 4 liter first, then it is allowed to contact for 21 hours, then it is drained out, then after completely draining, then it is allowed to kept in rest or dry condition for 3 hours. Then the cycle of fill, contact, and drain with rest is followed in this one. You can consider it as batch reactor. That's the difference.
I see. Thank you very much. So, let's me translate to the Indonesian language. So, teman-teman sekalian, para peserta, jadi pada pengolahan yang kedua dengan menggunakan rawa buatan atau constructed wetland, Amit Sensei atau Dr. Amit menggunakan dua pendekatan, yaitu pertama continuous flow. Continuous flow itu berarti ada aliran masuk dan aliran keluar. Yang kedua menggunakan tidal flow. Tidal flow itu adalah ketika dia masuk mirip sama batch tapi dia agak berbeda sedikit. Dia ada waktu tinggalnya dulu, jadi dikontakkan selama 21 jam, lalu dikeluarkan airnya, baru didiamkan anunya, baru dimasukkan lagi. Jadi sebegitulah pengolahan yang dilakukan. Dr. Amit, I would like to ask another questions. What is the effect of zeolite if we change to another media? So maybe the question is, if we change the zeolite, is there any possible effect of the constructed wetland?
Yeah, sure. Here the zeolite acts as the adsorption media. Like first the ammonium is adsorbed, then the adsorbed ammonium is oxidized to nitrite and nitrate. If we don't use the zeolite or any other media that doesn't have the ion exchange capacity or cation exchange capacity, then we have to depend barely or only on the nitrification and denitrification. So as we see in the continuous flow, yeah, this one, if the removal is here in the continuous one, the removal for 21 days is due to the adsorption on the media. If we don't use the media with adsorption capacity, then the removal would depend on the nitrification and denitrification only, so it could reduce the removal efficiency.
Thank you so much. So, did you measure the size of the zeolite?
It was, I just forgetting, maybe 4 to 6 mm, but we used 8 liter of the zeolite. 8 liter of zeolite in up to 600 depth, 600 mm depth.
Oh, I see.
So, and in bottom we used pumice, a bit bigger pumice for the porosity draining purpose. Here we have small layer of pumice of 20 mm only.
So the last question is there any possibilities that absorption also involved in the treatment process?
Sorry, would you please repeat the question?
The question is there any possibilities that absorptions involve the process? Absorption involve the process. Is it any possibilities for absorptions because you use the zeolite?
Adsorption, yeah, with the zeolite, I think this slide could, yeah, this one. Basically zeolite are the aluminosilicates with the negatively charged surfaces, and the ammonium we have the positively charged, so it gets adsorbed on the surfaces of the zeolite.
Thank you very much. That's the last question for yours. Thank you so much for your presentation and your answers. So I would like to translate again. So dari penelitian ini menariknya adalah bahwa dia menggunakan zeolite dan tanaman. Jadi ada faktor dari absorpsi dan faktor dari nitrifikasi dari bakteri sehingga bisa treatment dari nitrogen yang ada. Okay, thank you so much for Amit Sensei for your kind presentations. So we will go to the. Thank you so much. Konnichiwa.
Thank you very much for giving me the chance. It's a good time for interaction with you guys. Thank you very much.
Thank you very much. We will wait for your next presentation. Maybe next time you can come to Indonesia.
I hope so.
Okay.
I would love to visit Indonesia.
Yes. With your friend Rubiatno, my colleague, when I was first degree.
Yeah.
Thank you so much.
Yes, thank you very much.
So for the second presentation, we have presentation from Dr. Zulkarnaini. Dr. Zulkarnaini is Associate Professor at the Andalas University. He is the head of graduate school for environmental engineering. His research is about Anamox. Anamox is uh, an aerobic ammonium oxidation. He graduates from the Kanazawa University. So, Dr. Zul, could you hear me?
Yes, yes, I can hear your voice clearly.
Okay, thank you so much. How are you, Dr. Zul?
I'm fine, thank you.
Dr. Maybe I call you Zul Sensei as well because you graduated from Japan University, Kanazawa. So, uh, you can start your presentation. The floor is yours.
Yes, yes, okay, okay. Um, Assalamualaikum warahmatullahi wabarakatuh, and good morning for the participant and moderator, also Amit Sensei, who already presented his research. It's related also with my research, and maybe my presentations will continue about nitrogen removal also. But unfortunately, the camera in my laptop doesn't work properly. But today I use two laptops. One laptop for the speaker and for the mic, and the other is for the camera. So you can see my account to see my face. Okay, I will share my presentation now. Please confirm if you can see my PPT. Okay.
Okay,
Okay.
very good.
For for the beginning, I want to say thank you for Dr. Fahrizal Adnan. We met at Kuala Lumpur in a international conference. And the time we discussed about some research and collaboration research for Indonesia after we graduated from doctoral course. Today I will present not my doctoral research, but postdoctoral research after I graduated from Kanazawa University. At Kanazawa University, my research is about one-stage nitration Anamox for nitrogen removal in the water. After coming to Indonesia, I continue my research also about Anamox, but the problem is how to find the Anamox bacteria. Even at the time I bring 20 milliliter Anamox bacteria, genus species Candidatus Brocadia sinica. Many literature already available about Anamox, but in Indonesia, very limited information about Anamox. So this is a change for any researcher in Indonesia to start explore the existence of Anamox in Indonesia, the bacteria and the abundance. And for the ultimate is how to apply this bacteria to reduce or remove nitrogen from water, also from wastewater. For the introductions, maybe in our class, when we give a lecture, we talk about nitrogen cycle, but our current nitrogen cycle already developed rapidly because the discovery of new Anamox species or new process in nitrogen cycle. For the example, in the past we know about nitrification and denitrification, how to remove ammonium into nitrogen gas in the aerobic condition for nitrification and anaerobic condition for denitrification. But today, start from 1995, new process discovery. The name of the process is anaerobic ammonium oxidation. And the bacteria who play the role in this process is Anamox bacteria. For the chemical process combined with biological process and the involved bacteria, it's not like a simple of circle, but it's transformed to be nitrogen network because so many process and so many bacteria involved in this process. You can see from this figure. And today there are also a chance for us to discover new process or new bacteria involved in this process in nitrogen network. For the applications, biological nitrogen process is more efficient and low cost process, like explained by Dr. Amit. But in the condition of ratio C per N high, nitrification and denitrification can be applied to remove the nitrogen. But how about the wastewaters that contain high concentration of nitrogen, where the ratio C per N is very low? Nitrification and denitrification cannot be completed. To complete the process, it needs additional of organic carbon. Usually in the applications, they use methanol or ethanol to complete the nitrification and denitrification. The cost for the additional organic nitrogen will be high and the process will be not so efficient. Let we compare the nitrification and denitrification process versus Anamox. This cycle is a full process. For nitrification and denitrification, it needs more aeration because need to complete conversion of ammonium into nitrite and nitrate, and then with the existence of organic carbon, nitrite convert into nitrogen gas. But Anamox process can be cut 50% of the process because this process doesn't need more, can decrease 65% requirement of oxygen. Also doesn't need additional of organic carbon. It's also, this process can cut 50% of the cycle of nitrogen removal into nitrogen gas. And this process also produce less sludge production and less NO2 gas. But in this process, we can see there are two stages in Anamox process. The first is how to convert 50% ammonium into nitrite in the aerobic condition, and the second is Anamox process. The remain ammonium and the produced nitrite will be converted by Anamox bacteria into nitrogen gas in the anaerobic condition. In the application, usually there are two types of reactor. The first is partial nitrification reactor, and the second is Anamox reactor. But the new type of reactor is one-stage nitrization Anamox, where both nitration process and Anamox process take place in only one reactor. And that research is my doctoral research. But today I will talk about how about Indonesia. you can see from this map, this is the reported the existence of Anamox bacteria in the world. This is reported. I mean, in the many countries in the Southeast Asia, also Indonesia, there is no report about the existence of Anamox bacteria. Even this bacteria, the role is bacteria is very significant to remove nitrogen, 65% nitrogen in the sea, also in the water, wastewater, also in the lake, in the river, and many ecosystem, water ecosystem in anywhere, but the reported is limited. Today, there are 7 genera of Anamox bacteria. Anamox globus, Quininia, Brocadia, Scalindua, Anamox microbium, and the new one is Bacillus. It's new genus of Anamox bacteria that find in the Brazil. But there is no report in Indonesia, also in the Southeast Asia. Report mean about the research. It means at this location or the country, research about Anamox may be very limited, or there is no report about Anamox bacteria in the place. The lack of the challenge of application and research of Anamox bacteria is the type of the bacteria. This bacteria is very slow growth bacteria. The doubling time is about 10 until 30 days. For the bacteria, it's very, very low. If we compare with E. coli, it's maybe in 1 minute. We can produce so many bacteria, but Anamox bacteria, the doubling time is very high. To solve this problem, usually many researchers try to cultivate or enrichment Anamox bacteria from the environment using so many type of reactor. For example, upload column reactor, sequencing batch reactor, and the new one is membrane bioreactor. And membrane bioreactor is powerful tool for enrichment Anamox bacteria, but this reactor is very complicated. Yes, it's very complicated. If we buy in the market, the price will be high, and the operation is maybe a little bit difficult. For the application, previously we talked about research, and now we talk about the application. Today, more than 140 full-scale Anamox reactor operated in the world. We can see the dot is mainly in the Europe, China, little in America, but there is no dot here in Indonesia or Southeast Asia, or we can say this is generally in developing country, because the developing country, the concern about nitrogen. The concern is about organic carbon, but the nitrogen is very limited attention about how to remove this parameter from the water. We can see the installation of an operation of full-scale Anamox bacteria mainly in the subtropical country, and Indonesia, except Brazil, India, Pakistan, or Southeast Asia, is in the tropical country. If we operate Anamox process here, the cost will be high. How to maintain the temperature, especially in the winter. But in the equator, tropical country, we should not regulate the temperature, because the average temperature is warm in the tropical country. And this is a change for application of Anamox bacteria. The impact of the excess of nitrogen in the water or water body in the tropical country, there is common phenomena we can find anywhere. That is eutrophication. Eutrophication for the application of so-called water, for example, for wetland, also this method applied. But in the environment, we can find so many eutrophication in the water body. This is my hometown, and the place we do the research to explore Anamox bacteria. The higher ammonium concentration in environment could be indicator also the existence of Anamox bacteria. This is the point of our research. The higher ammonium concentration in the environment could be an indicator of existence of Anamox bacteria. So we hypothesize, our hypothesis is Anamox bacteria live in this eutrophic lake. For the first analysis, we try to analyze the characteristic of water of Kota Baru Lake in West Sumatra, Indonesia. Also, we take sample from the sludge. We can find that the water of Kota Baru Lake containing both ammonium and nitrite, also nitrate. Because ammonium and nitrite is food for Anamox bacteria to convert them into nitrogen gas. What about the reactor? If we buy the reactor, like membrane bioreactor, the price will be very high. The price will be high, maybe 100 million rupiah. But in this experiment, we can very cheap material, string wall filter and housing filter. We can find anywhere. In Indonesia, there are refill for drinking water. The cost for this reactor only $5. $5 is very cheap. We operate two reactors. First reactor we operate in room temperature without temperature regulation, and the second we put in the incubator with 65 degrees Celsius. This is we operate two reactors, and we suppress substrates that containing ammonium and nitrite, and we check the influence and the effluent. Then we take samples. We take sample from only for 4 points. We take sample from the 4 points because the lake is very shallow. The deep only 1 meter until 1.5 meters because of the accumulation of the sediment. We can maybe sludge is better because when we take the sample, it's not sand, but it's soil in that in the floor of the lake. We take 4 samples, and this is the picture of our sampling location. If we take from Google Map, and the water is covered by the plant. And for the sampling, we use very traditional shape like bamboo raftings, but it is not safety for the samplings. And we operate this reactor for 200 days. 200 days. At 2 months, first 2 month operation, maybe we very sad because we find the effluent of ammonium higher than in influent in both reactors. This is very sad result because maybe we will be fail with our hypothesis, maybe no Anamox bacteria. But after 2 days, 2 months operation, we put out all the sludge because for the shedding startup this reactor, we use shedding the sludge about 25% of the volume of the reactor. Then after 2 months, we put out all of the sludge and we operate again. Why we put out the sludge? Because even the concentration of ammonium is higher than in effluent, but nitrogen concentration is decreased rapidly and stable. Maybe so many processes occur here, but our purpose is only Anamox process. Then we put out the organic carbon to make clear this process is Anamox or not. Then after we put out the sludge, we can see clearly both ammonium and nitrite removed from our reactor in reactor 1 and reactor 2. then we look at the nitrogen removal from both reactors. We find the new finding from this data. Usually, Anamox process optimize in 25 or 45 degrees Celsius. But in our experiment, the better operations of this reactor is in room temperature without temperature regulations. It means the performance of nitrogen removal in the room temperatures is better compared to in incubator. It means we not need to regulate or control the temperature to remove nitrogen. One of the specific biomass of Anamox bacteria is the color. The color is red charming. At the beginning, the color black, but we can compare both of reactor after 20 days operation. In the left is in the incubator, and in the right is in the room temperature. In the room temperature, the color is changed from black at the startup become red charming. Then we take the biomass for microbial community analysis to ensure that this biomass is Anamox bacteria or not, or a small amount of Anamox bacteria or the dominant Anamox bacteria. In Indonesia, we cannot analyze the sample, even we also finding that or other institutions or other laboratory or other university, we cannot find the place for analyze. Then we bring the sample to Kanazawa University for microbial analysis using Illumina MySeq sequencing. And the result is very interesting. In the film level, the more abundance of phyla is similar between run 1 and run 2, Proteobacteria, Planktomycetes, and Bacteroidetes. But there are one of the others in run 2 is Acidobacteria, also abundance at run 2 only, but in run 1 is relatively low. This Anamox bacteria is belong to Planktomycetes. Look at the genus level. At genus level, we feel surprised with this result because we find two genus of Anamox bacteria. First is Brocadia with 3 genus, Brocadia 1, Brocadia 2, and Brocadia 3. Brocadia 1 is more abundant. Brocadia in run 1, also Brocadia 2 in run 2, but the abundance is decreased if we operate in the room 35 temperature. It means this species of this genus is better life in the room temperature without temperature control. And also we find a rare of Anamox bacteria. Candidatus anamoxoglobus is a rare Anamox bacteria. Very little reported the existence of this Anamox bacteria. And here we find it. Look at the similarity. We use Aerobic software to compare the similarity, our sequence with the existence of known Anamox bacteria. And we also, the result is very interesting. We can say there are two novel Anamox bacteria because the similarity only lower than 65%. Lower than 65%, lower than 95% means maybe this sequence is new bacteria. The FTBR4 is 85 only, and with similar with Candidatus Brocadia caroliniensis, and the others is the similarity only 65. This is novel, and we already make the draft. For the next experiment, this is experiment of my student. We compare. Previously, I bring Candidatus Brocadia sinica from Japan, and I operate in room temperature for 1 year. for 1 year. Oh no, this is 2 years. And this in the right is Candida subrocadia sinica. In the left is in novel Anamox from our cultivation reactors. And the result is very good, because the nitrogen removal rate is increased rapidly. But in the Candida subrocadia sinica, at the beginning, there is no nitrogen removal appear, but after 25 days, the nitrogen removal increase, because Candida subrocadia sinica, the optimum performance is in the 35 degrees. Okay, this is my contact for future discussions. I hope we can collaborate in this research. And my dream is how to build a full-scale Anamox bacteria in Indonesia using native Anamox bacteria. Compare, we should buy or import the bacteria from the outside and bring it here. The cost will be high. We can do it by ourselves and by our skill and collaboration also. Thank you for your attention. I return the time to the moderator. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Zul Sensei, for the very good presentation and very interesting research. Ladies and gentlemen, all participants, both of the sensei is talk about the treatment of nitrogen. The Zul Sensei is talk about the ammonium treatment using the Anamox. Let me translate in Indonesia. So, Dr. Zul ini penelitiannya tentang Anamox. Anamox itu adalah anaerob ammonium oxidation ya, oxidation. Jadi dalam proses pengolahan amonium biasanya kita menggunakan nitrifikasi dan denitrifikasi. Misalnya adalah pertama stepnya merubah amonia menjadi nitrit dan nitrat, lalu merubahnya dengan denitrifikasi menjadi nitrogen bebas. Ada 2 step biasanya dilakukan, tetapi dengan menggunakan Anamox maka dari amonia bisa diubah menjadi nitrogen dengan bakteria Anamox spesifik. Ini penelitian yang dilakukan oleh Dr. Zul. So Dr. Zul, we will open the question and answer sessions. The first question is, what is the obstacles to grow Anamox bacteria in Indonesia?
Okay, I will answer directly. The obstacle of application of Anamox bacteria is the first is about the research. Limited research about Anamox. Also, the expert. Research is mean also expert. Limited expert about Anamox. There are one paper about Anamox, but she bring the bacteria from Osaka University also. After personal contact, the researcher does not continue her research about Anamox. So we need to start many research about Anamox. Then we can do other step for the application of Anamox bacteria. For Anamox group, maybe in Indonesia, if I mistake, please confirm. There is only one group Anamox in Indonesia now, and it's our group Anamox in Andalas University. And we hope many group Anamox will be conducted in many universities in Indonesia. Then we can do next step for application of Anamox bacteria. And our final target is full-scale Anamox bacteria with our native Anamox bacteria from Indonesia. And the second is the characteristic of the Anamox bacteria. Anamox bacteria is very slow growth Anamox bacteria. And the abundance in the in the environment is very low compared to others bacteria. If we compare with Nitrosomonas, Nitrospirae, or heterotrophic bacteria, the abundance in the environment is very high, but the Anamox bacteria, the abundance is very low. Also, the doubling time is 2 weeks, and 2 weeks until 4 weeks. For the bacteria, they grow 2 weeks and 2 weeks to 1 month is very, very, very low. For example, the first full-scale Anamox bacteria in the world is in the Netherlands. They start the reactor with volume 35 meter cubic using nitrification sludge, and it took 3.5 years to get high performance nitrogen removal. It's using nitrification sludge, but we can't increase the startup only for 1 month or two weeks if we use Anamox bacteria for the seeding sludge to start up the reactor. So the solution is we should enrich the Anamox bacteria in the laboratory first, then we can apply it to treat wastewater treatment. And for the application is not so difficult because we have so many experts about about biological process, expert about chemical engineering, expert about chemical engineering. So we should do it together with many experts.
Okay. Thank you, Dr. Zul Sensei, for the answers. So I agree for the answers that the still low research, still limit, still a few research about the Anamox treatment process in Indonesia. So I still remember I have a promise to the Dr. Zul to make the research proposal about the Anamox because I'm very interested to this research. And then maybe in the near future, I will ask many questions to Dr. Zul how to implement the Anamox process in the Mulawarman University. And maybe with the Amit Sensei as well, we can make the collaborations between the Nepal, Andalas, and Mulawarman University to make the specific species of Anamox, especially in the tropical area. So the next question is, so we cannot use the Anamox bacteria from the Four Seasons country. Is it true?
What from?
So maybe the question is, we cannot use the directly from Anamox bacteria from the Four Seasons country, like the subtropical, and then implement in Indonesia directly, right? So what is the problem with these conditions of bacteria?
Oh, I see. So many type of bacteria, so many type of Anamox bacteria, and they have wide range of temperature for grow rate. This is for grow rate, the range temperature of Anamox bacteria very wide, maybe from 0 or minus until 45. This is for grow rate, not for optimum performance. We can bring Anamox bacteria species from other country, from subtropical country. For example, Anamox bacteria species Candidatus brocadia, Anamox microbium, Anamox globus, Bracilis, so many types of bacteria. But the problem is the cost. The problem is the cost for transportation. And the other problem is the adaptation of the subtropical Anamox bacteria who live in the subtropical country to the Indonesian tropical country. This is the idea of our research. Why we should bring Anamox bacteria from outside to Indonesia? Because Anamox bacteria live everywhere in the many ecosystems in the world, in Nepal, in India, in China, in Australia, in Indonesia also. Because Indonesia is tropical country, maybe bacteria, many bacteria live here with higher abundance. Then it's better we can, maybe in the Kalimantan, they can find their own native Anamox bacteria and analyze the sequence. Maybe many new Anamox bacteria live there from the wetland in the Kalimantan. And for our experiment, we take from autophagic lake, we can find it. And after that, we can enrichment the bacteria for multiplication of the biomass, and we can treat for wastewater treatment. For example, today we analyze the bacteria from wetland, from fertilized industry, and we cultivate it in our laboratory, and we identify the species. What the final purpose of our research? Our final target is we want to replace the wastewater treatment facilities from wetland that use very large area to remove nitrogen into very small reactor. The small reactor is Anamox reactor. Then we can optimize the other land for other utilities. Compare only very wide area to treat the wastewater more efficient with the small reactor. The reactor is Anamox reactor, and it's better to find it to identify and enrichment Anamox bacteria from Indonesia, and we can do it, and we already proved we can do it.
Okay, thank you, Zul Sensei, for the answer. So this is like a breakthrough research about the Anamox because it's still low research, very few research in Indonesia about Anamox. So we will very open if you want to participate in the research about the Anamox. So the next question is, what method to analyze the Anamox bacteria species? Why we cannot do it in Indonesia?
We can do it in Indonesia. The instruments already available in Indonesia. The Illumina MySec sequencing available in the Batam, also in the LIPI, but the instrument used for agriculture. I mean, for agriculture, or maybe for agriculture, but not, they cannot accept the sample from the outside the institutions. We can do it by ourselves. If the university purchase the instrument, and we can do it by ourselves. Also, if we send a sample for analyze, the price for the service also very high. But this is not obstacle of Anamox research. We can collaborate with other university in the outside. For example, in Andalas University, we collaborate with Kanazawa University for microbial community analysis, and the service is free for analysis, and we can join publish our finding in the high-ranked journal. And now we in the submission process to publish our finding. We can do it if the instruments available. But for enrichment Anamox bacteria, the first step is not for analyze. The step is to explore and find the bacteria. To find and explore the bacteria. And to find, to explore, and to enrichment is very, very simple, using very cheap materials for the reactors. And anyone can do it. And anyone can do it in Indonesia. Just we should be work hard, and because the experiment for the Anamox is cannot be do in short time. For my students, they do the experiment for 1 year. Maybe for undergraduate students, they don't want to do the experiment because they want to graduate as soon as possible. It is the problems. The student can want to graduate as soon as possible. Okay.
Thank you, Dr. Zul, for the answers. The next question is, what is the influence of phosphorus? Because in the environment, we not only find the ammonium, and then we have the phosphorus as well. Is there any, how to say, the scavengers effect of the phosphorus in the process of the Anamox?
Okay. Phosphorus is the element. Phosphorus is special element. It means it cannot, because we cannot find phosphorus in the gas phase. In the gas phase, there is no phosphorus in the gas phase. The phosphorus we can find in the solid or dissolved from the water. How to remove it? How to remove? Yes, we should to precipitate to convert dissolved phosphorus into solid using precipitation, using chemical process. But we have also find interesting results about phosphorus. Look at this. Wait, I will share this. I will share this presentation. Okay, look at this microbial community analysis at genus level. Look at the run 2. This is 11%, the abundance. This is the second dominant of bacteria in the run 2 were operated in 35 degrees. We can find PHOS. This bacteria is phosphorus removal bacteria, grows in our reactor in the 35 degrees. This bacteria can be used to convert phosphorus with the existing organic carbons. In some literature, they conclude this bacteria can be used to remove phosphorus. We do the next research about this bacteria. Now we increase the concentration of phosphorus in our reactors to observe the phosphorus removal from our reactors. In the fertilizer industry, the temperature of wastewater is 35 degrees. In our experiment using seeding sludge from wetland or wastewater treatment facilities in the fertilizer industry, we find the white not biomass, white sediment or white sand in our reactors. But we cannot show this result today because we need to do the future experiment to prove our finding. But in our abundance, we already enrich phosphorus removal bacteria. And for this finding, we will do next experiment, how to remove nitrogen with also phosphorus in one reactors. Maybe for next webinar we can publish our research.
Okay, thank you, Dr. Zul Sensei, for the answers. The next question is about this Anamox is kind of attached grow biological process. Yes, correct. Because in the biological process, we know the attached grow and suspended grow. What kind of media that we use in the Anamox process? What kind of media in the
Media. Okay. What kind of media?
Yes.
Usually, one characteristic of Anamox bacteria is self-granulations of Anamox bacteria. Usually, Anamox bacteria will be make will make a colony, and after that it will be make granule. Granule is with the size about 1 millimeter with the granule. Also, in the applications of Anamox bacteria, they use granule, and for media, others media is so many media, but the key of media is the media does not containing organic carbon. We also try to grow Anamox bacteria using bagasse. Bagasse is bagasse. Bagasse is containing organic material. In that media, in the organic media, the granule become the color become black. It means the Anamox bacteria become dyed because it competes with heterotrophic bacteria. Then so many non-woven carrier or media. We use filter, we use membrane filter, plastics as media. So many type of media that doesn't containing organic material, because organic material can be promote the heterotrophic bacteria, and the fast growth of heterotrophic bacteria can be Anamox bacteria can be outcompete, and the abundance will be very low. So many. In this experiment, just buy string one filter. String one filter, the price will be only $2. $2 for string one filter. It's very cheap. In our laboratory, we use the PET bottle. We use PET bottle as media also to grow Anamox bacteria in the form of biofilm. So the experiment is very easy. We already training the students and our collaborators from UMT, University Malaysia Terengganu, how to enrichment Anamox bacteria. They come to our university. If Unmul want to start the research about Anamox, maybe I can teach the researcher online. We can do it online also, and this topic research is very interesting. We get the funding from Kemenistek Dikti every year for this research, because this is new research, and the prospect is very high for the application in Indonesia.
Okay, thank you, Dr. Zul, for the answers. So, this is very open, how to say, it's very open for the another researchers, especially in the Kalimantan, Sulawesi. Maybe we can make the Anamox strains of Kalimantan, the strain of Kalimantan, the strain of Sulawesi, to make the Anamox, the native Anamox in our place. So, Dr. Zul give us the, how to say, can give us the online tutorial how to make how online lecture on how to enrich the Anamox bacteria. So the first step is we have to enrich bacteria in our place, and then we can apply in our lab, and then we can move forward to do another research about that Anamox, the implementation or something like that. So the media, we can use any media, but for the note is we have to make sure that no other bacteria live in the media. So for example, no organic materials. So make sure that no another heterotrophic bacteria live in there. So the next question is any influence direction of flow in the Anamox reactor, Dr. Zul?
Anamox?
Yes, because you use the bottom-up flow. Is there any influence of flow of the reactor that can affect the result of the Anamox treatment process? The flow of the...
Oh, the flow.
Yes.
The flow, so many types of flow, but commonly upflow used for the Anamox. Also, there are many types. Upflow or from the top to the down of the flow. Also about what we can say, there are the flow using vertical. Horizontal flow. Yes. And my research is using two flow. My doctoral course, I'm using one stage nitration Anamox using two flow. The first flow is into the hollow inner side of the filter, and the second flow is outside of the filter to the reactors. I'm using two flows. What is the purpose of the flows? The purpose of the flow is, the first is how to, this is because of what type of biomass of Anamox bacteria that we use. Because Anamox bacteria usually can colonize, become granules. So it will be settled in the bottom of the reactor. Then if we use upflow, the performance will be higher because 60% nitrogen removal in the upflow reactor occur in the bottom of the reactor. And the performance will be decreased with the increase of the height of the reactors. So commonly using upflow reactor. But if we use the Anamox bacteria in the form of biofilm, and we can use we use media, the performance will be distributed because the interaction of Anamox bacteria and the wastewater will be higher. We can use the flow from the top or the bottom, depend on what we want to using the flow. For it is the first time. This is related with the nitrogen removal performance. And the second is how to maintain, for my research, how to maintain the environment suitable for different of raw bacteria. In the one-stage nitration Anamox bacteria, we should regulate the oxygen because the oxygen is enough to growth of anaerobic aerobic ammonium oxidation. And also the oxygen should be limited not to kill the Anamox bacteria that the process occurs in the anaerobic conditions. In my experiment, I used two inflows to control the microbial community analysis. It's depend on the purpose, our reactor configuration. We configure the reactor based on our purpose.
Okay, so it's depend on the purpose. So that the media or something like that, it will be influence the flow of the reactor, Anamox reactor. I want to elaborate. So in your research, you use the filter housing, right? So the
Yes.
flow is like horizontal. So that is no problem if we use the media, if we use the horizontal flow. Yeah?
Horizontal flow. Horizontal flow usually used for other research. They use many compartments of
Oh,
the
I see, I
reactor.
see.
They use like IFAS,
Mhm.
integrated fixed anaerobics. Uh, they use sponge for media. So the wastewater flows into media in the horizontal the direction and the effluent, like the comment of wastewater treatment facilities for organic carbon or domestic wastewater.
Mhm. So the last question is, mostly in the biological process, we need to do the acclimatizations before we put the plant or the bacteria before we conduct the treatment process. Do we need to do the acclimatization before in this Anamox process?
Okay, I will answer. I will answer with my experiment when my students submit to journal Indonesia.
Mhm.
This is a journal in BPPT. And after submitted, the the editor, also the reviewer, give comments. This is minor revision,
Oh, I see.
minor revision, because um, Anamox characteristic of Anamox process different with uh, current microbial process, microbial analysis with current microbial community analysis. It's very different because Anamox bacteria cannot be enriched in pure cultures and cannot be growth in the plate using media or plating media cannot be cultivated at the media. This is a different view, a different experience for our examples. So for the questions, I forget for the question. Please repeat the questions.
The acclimatizations process.
Acclimatization.
Yes.
For the acclimatization is this is our funding. Our funding is it's better to use Anamox bacteria from native environment to apply at the area.
Oh, I see.
It's our funding because we already bring Anamox bacteria species Candidatus brocadia sinica from Japan, and we try to operate in room temperature, but the performance is decreased because that bacteria the optimum performance is 35 degrees until 30 until 45 degrees. But in our novel Anamox bacteria, we should not need to cultivate what? Cultivated, no cultivated.
I see.
Should not need to adaptations for the new environment because their environment is here.
I see. So it's kind of like for us, Indonesian is Indonesian is tropical people. So if we go to the Japan, we need to acclimatizations, right?
Adaptation.
Because the weather is very cold. But when we live in Indonesia, we feel it's okay, it's normal. So it's same like the Anamox bacteria. If we
Yes,
live,
correct.
if we enrich the bacteria from Kalimantan, from Padang, it will be in the like the normal environment for them, yeah, right? So we can use it directly, not like the another species that we need to acclimatization first,
Yes.
and then need another process before the treatment process. I see. This is a very good funding and a very good answer from the Zul Sensei. After that question, it will be the last questions for these sections. I would like to extend our gratitude. Thank you very much, Dr. Zul, for your very nice presentations.
You're welcome.
And then also I would like to also thank you again to Amit Sensei from the Yamanashi University.
Thank you very much.
Thank you very much. After that presentation and Q&A answers, that is the end of the webinar today. I would like to say thank you to all participants, especially the speakers today. I hope we will make another research together about the nitrogens, and then based on our area, Indonesia, Nepal, and Japan, and then we make keep moving forward for the research about the nitrogens. And then thank you very much, and at least that all. Okay, thank you so much, and I would like to say thank you, and then I will close this webinar with wassalamualaikum warahmatullahi wabarakatuh, and very good morning.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you Amit Sensei, Zul Sensei.
Okay. Izin dulu.
Jazakumullah khair.
Ya. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you.
Hello. Hello.
Hello. Yes.
Sensei is there.
Yes. It's.
Yes. Last time, did you visit Osaka for the WET conference?
Oh yes.
I think I met you there.
Oh yes. Oh, I remember you. I did Kumar. You asked me about Anamox.
We talked about Anamox, right?
Ah yes. How are you? Already graduated?
Yeah.
Oh, alhamdulillah. So you know a lecturer in Yamanashi?
Yeah, I still am Yamanashi.
Oh, it's good position. Okay, probably we will next. I already attended the WET conference in 2020 now. Online also. It's online. Do you